you for the introduction. And it's very exciting for me to be here with you today and kind of step out of my usual cycle of nuclear industry presentations and hear about a lot of different ideas. And so I've enjoyed all of the presentations today. I wanted to talk to you a little bit about what's going on in the nuclear industry through the example of what I know best, a new type of nuclear power plant that we're developing at TerraPower. First, maybe just a couple of things about TerraPower, because it's an interesting company in and of itself. The company was formed by Bill Gates back in 2008. Really just a small group of people that were asked to go off and look at a potential solution to global energy poverty. So that's really where it all began, was a real interest in trying to help lift the standards of living across the world where people can't get access to energy. It wasn't necessarily a mandate to go look for a nuclear solution to that, but as Bill's technical advisors did the research, what they found was there was a lot of technology in the nuclear space that had not been fully commercialized. And in fact, there was a type of nuclear reactor that went through a lot of research and development in the United States for multiple decades in our own home state of Washington that really never reached the commercialization stage. It was paused in the 1980s and never went any further. And it was thought to have the most promise because of its close to commercial readiness. And one of the things that was holding it back was a couple of things. There were a lot of technical innovations still needed with that technology to make it commercial. And one of them was a high performance computing power, which of course, Bill Gates knows about really well and thought that he could bring that type of solution and unlock the power of this technology for the world. So that's what kind of turned us on to nuclear power. And through that, the concept has been further developed and adapted to meet the needs of the future electricity grid. So my purpose today would be to talk to you about this technology, what's new about it, what can it do for us today, and turn that around to how it affects grid resilience. So just, right off the bat, the name of the reactor design is called natrium, after the Latin word for sodium, which gives us our elemental symbol in the periodic table. What it is it's basically a nuclear power plant with an integrated energy storage plant attached to it. And it was really developed to address some of the main challenges of the nuclear industry that some of you may know about, the constant need to improve safety, which is the #1 priority, but also to reduce the costs, both of operation and capital costs that have held nuclear back from being further commercialized, and adapting it to be more flexible to the modern electricity grid. And so those were the main drivers behind this. And so, as we look to natrium, one of the other things that was required was to actually address another aspect for the United States in particular, which is energy sovereignty. And so the nuclear industry has kind of grown dormant in a number of ways. The supply chain has grown dormant. Even the supply of fuel has grown to where we now get that from outside the United States. And so when we formed this program, one of the other goals was to reestablish that supply chain and the energy independence that comes from making our own fuel and maintaining leadership in advanced nuclear technology in the United States. And so one of the things I'm very excited about with this is it's just a whole new structure to a large nuclear project that I don't think has ever been done before, because natrium is supported 50% by the federal government and 50% by TerraPower private investment. So it's a cost share, project that involves a number of collaborators, including PacifiCorp, a number of universities, national labs, and other companies and suppliers that are all coming together to build this project. We broke ground back in June in Kemmerer, Wyoming. So things are now happening at the site. We've been going on the project since 2020, getting all of the design mature so that we can reach this stage of breaking ground. So now we have really 3 paths going on the project. We've got the design still moving forward. We've got a construction permit application with the Nuclear Regulatory Commission that's going through review right now. And we have the construction site with ongoing activities. So now it's a really active project. But what it does is it takes both the private investment and the federal government to pay for the first of a kind development costs for this new technology. so that future reactors can be sold at a commercially competitive price. And that's one of the real things that advanced nuclear really needed to kind of get off the ground and lift off, so to speak. So just looking at the picture of the site layout and just trying to help you appreciate what the plant is. It's essentially a nuclear island and an energy island. That's what we call them. And I think the best way to get some appreciation of what's going on here is to talk about the flow of heat. So essentially, we're generating heat in a nuclear reactor that is essentially below ground within what you see as the reactor building located in the center of this plot. So the heat is generated in the nuclear reactor, and it's then delivered to the reactor auxiliary building that you see just below it on the graph here. And then that heat is transferred from the coolant in the nuclear reactor to a molten salt energy storage system, and then delivers that molten salt over to the energy storage tanks, those two white tanks that you see on the right. And so one of the new things here is that the energy is stored there in those tanks as a reservoir of energy before sending it to the steam generators to generate steam to go to the turbine to generate the electricity. So, you know, everything from the steam generation building out to the turbine is very typical of any power generating facility that you see. It's a typical Rankine cycle, except it's got a nuclear reactor and it's storing energy in these tanks before generating the steam. One of the other unique things that we've done that's really new for a nuclear facility is we've now drawn some boundaries. We've got an orange boundary around the nuclear island and a blue boundary around essentially everything else, which we're calling the energy island. And what we've done is we've decoupled these two things from one another so that the nuclear reactor doesn't rely on anything in the energy island for safety. Essentially, all of that equipment could just disappear and the nuclear reactor would still remain safe. It would shut itself down and it would continue to remove whatever heat was left indefinitely with no need for anything else from within the blue boundary. And so that was one of the key things to do this decoupling. We've had this architecture approved already by the Nuclear Regulatory Commission. And what it allows us to do is really minimize the footprint of nuclear equipment that you have in the plant, which really reduces the capital costs. It also allows for more flexible operation than you've ever been able to have in a nuclear plant, because the energy can be dispatched from the energy island without going and talking to the nuclear operator about that. And nuclear plants have never been able to quite do that, because in today's plants, if you take the turbine away, you affect reactivity in the reactor system. And so you can't do that independent of the reactor. But what we've done here with the energy storage is we've decoupled these two things from one another. So now the Nuclear Regulatory Commission doesn't have to provide any oversight within this blue boundary. So we've really reduced the costs of operating and maintaining the plant going forward. Another thing to talk about is just the different kinds of coolants. So the nuclear reactor here, instead of using water for cooling like current plants do, it uses a liquid metal in the form of elemental sodium. This is not, it sounds exotic, but it's really not, because the US has run sodium reactors for about 3 decades, and we have a lot of that experience to draw from, and it's used around the world in many different countries as well. But it is new when you start to think about it based on our water-based experience today. And so what's great about that is that sodium as a liquid metal is great for removing heat. You probably know that just from your experience cooking. You know, metals like to conduct heat. So it's very good at giving away the heat and keeping the reactor cool. And then the energy is stored in the form of a molten salt over in the energy island. It's actually the same kind of energy storage architecture used in concentrated solar plants today. If you look at a Solana or Crescent Dunes plant, they're going to have the same type of equipment. The exact same type of molten salt composition is used. So we're using a lot of that industry standard equipment for this side of the plant. And molten salt loves to hold on to its heat. So it doesn't lose heat very much. In fact, the energy island could be put much further away from the nuclear island if we wanted it to, in terms of if we were to use this for delivering heat to industrial customers. You might want to have the energy island close to the industrial customer and the nuclear island further away. You have that flexibility with this type of architecture. So just a real quick look at the nuclear island. If we center in on the 3 main buildings in the middle of that plant layout, and you look at it from a cross-section view, you can kind of see the nuclear reactor core is this small little square at the very bottom of the graph here. And the purpose of this architecture is to keep all radiological material below ground. They're all below grade. The nuclear reactor is completely below grade within a seismically qualified nuclear containment structure. And then everything above ground is really industrial grade. You don't see a large pressure retaining concrete containment building with 1 meter thick walls or anything like that, like you see in today's reactors, because everything is below grade and it's already protected. And the other thing is that sodium can remain at a very high temperature at atmospheric pressure. So all of these systems are low pressure systems. We don't have to build them to contain that energy from the pressurization of the nuclear reactor. And so that's one of the main benefits of keeping costs down and making this reactor have a really small nuclear footprint. So now to turn it around to look at the grid and what we've been thinking about with regards to how this system can impact grid resilience. I'm sure you're all familiar with this sort of intermittency problem that you have with renewables, but this discussion is to kind of set up the characteristics that the energy storage system needs to have by looking at what's happening on the grid. And so what this is some grid modeling that TerraPower did a while back from the Western Energy connection. And it brings in data from that, but also projects it out, a decade into the future. And it's showing you 2 days of data on each plot. The left side is summer and the right side is winter. And so you just see some patterns here. The blue and the orange curves are showing you the wind and solar energy generation, and the gray is showing you the residual demand after all the wind and solar have been used. And so what you see here is kind of typical in the summertime is you see wind and solar meeting most of the demand during the daytime hours with just maybe a little bit left over. And then when those assets start to come offline towards the evening hours, you see this very fast ramp where a new asset is needed to come meet that residual demand. And the slope of that ramp is really important to us in thinking about how to design our plant to address this problem, as well as the duration of that peak and how long it's going to last. So we've got to design our energy storage system to meet the ramp requirement and also meet the duration requirement of that. So that's pretty typical of the summertime. In the wintertime, what you see different there is that the shorter daytime hours provide additional volatility. So now you could have a ramp needed in the morning and in the evening. So you could have to do this not just once, but twice a day. And so it really is a big demand on that energy storage system. And typical nuclear reactors that you see today aren't set up to load follow at this type of frequency where you're doing it multiple times a day. They are designed to do it maybe once a month, twice a month, or at a slower rate, but not at this type of requirement. So that's what we started looking at with Natrium. And so it sets us up to consider what this energy storage system really has to provide. And so whereas the nuclear island, we want to be completely standardized. We don't ever want to change the nuclear island. We want to keep it running 24/7 at full power all the time. Nuclear assets provide great baseload energy generation. They're really good at that. We want to continue to do that. But on the energy island, we have lots of different options, and we want to do all of this very frequent load following. So what you see on the graph here at the top is you see the energy island looking from as if you were standing on the nuclear island. You see the pipes carrying the molten salt from the nuclear island into the 2 storage tanks. There's a hot salt tank and a cold salt tank. And then, the pumps from the hot salt tank are used to send molten salt to the steam generators to generate steam for the turbine. So this is showing you one configuration that we're using in Kemmerer, Wyoming, where the nuclear island is providing a base load of 345 megawatts electric all the time. And then the energy island is able to ramp up to 500 megawatts electric for about 5 hours. And it can do that twice a day, every day. So that's essentially the Wyoming design. But if you wanted more energy storage, you could just add additional pairs of tanks. If you wanted to have a higher peaking, maybe 500 wasn't quite high enough, you could provide additional tanks, and you could also size your steam generators and your turbine to go up to higher peaking values. So you have all those options to consider. The ramp rate in this design is really limited by the turbine. So if you wanted a higher ramp rate, you could actually just pay for a more expensive turbine to get you that if you wanted that. For example, on the left side, you see an aerial shot of a concentrated solar plant, and you can see they have a number of different molten salt tanks there for additional energy storage duration. So what are some of the properties of, when we look at the ramp rate, there's a number of things to consider. I'm kind of showing you a number of different types of energy generation on this table. There's a couple of nuclear ones up in the top two rows. The AP1000 is a large nuclear reactor. The two that were just built in Georgia were AP1000s. You can see the ramp rates that they provide at this daily frequency, okay? They can go faster at like a monthly frequency if they needed to, but I'm showing you data for like an everyday type of load following. NuScale is another type of small modular reactor. We've got coal listed here, and these are just typical representative values. And we've got some combined cycle plants listed on here too. And so what we really wanted to do was be competitive with all of these fossil fuel generating assets and better than any of the existing nuclear assets by using this energy storage system. And so we've sized it to provide a 10% per minute ramp rate. We think that's the ideal place to be in terms of cost benefit between, you know, how expensive the turbine is and how fast you need to have for the grid that you're looking to operate within. So this is an animation, and you'll see it start to kick in here in a minute, just to give you kind of a sense of what is going on when you're trying to load follow with energy storage on a nuclear plant. And what you'll notice, this is taking data from Japan, actually, and it's covering all 4 seasons of the year. So the curve on the right will continue to shift as you move through these different seasons. But what you'll see is that the reactor power in the red is always constant. So that's going to be a constant energy generation of 345 megawatts electric. And then you'll see the energy generation in the black bar continuing to change to meet the demand. And then you'll see the inventory of fluid in the salt tanks continue to shift. And so load following is just a matter of inventory manipulation between the hot salt tank and the cold salt tank. If you want more steam generation to generate more electricity, you simply turn the flow rate up on the hot salt tank pumps to start sending more hot salt to the steam generators. That will deplete the hot salt tank to a level eventually where you'll have to stop that. You'll have to throttle that back, come down, reduce the hot salt flow so that that tank can recharge itself. And if you're a nuclear operator, you're looking at the inventory of the cold salt tank because that's allowing your nuclear plant to continue to cool itself using the molten salt coming into the nuclear island. So if that cold salt tank inventory gets too low, you've got to do something on the nuclear plant to turn the power down on the nuclear plant. So you never want to do that. You want to keep the nuclear plant always 24/7 by manipulating the inventory back and forth between them to meet energy demand. So that's essentially what's happening when we talk about load following. And then I wanted to close with just, you know, thinking about this at the system level, because there's clearly benefits at the individual plant level to lower the costs of nuclear, to provide the added value of energy storage and being able to do this load following. But there's also advantages when you look at the system level at reducing overall system costs for deploying a fleet of, say, renewable energy as well as nuclear with thermal energy storage. So this organization, Breakthrough Energy, did some grid modeling to look at this. And so this is showing the results of their study. In a case where, again, on the Western Interconnect, if you had to go to 90% carbon-free energy and you had to use only renewable energy now, the left side of that shows that you would need over 12,000 gigawatt miles of new transmission capacity. On the right, they looked at the same deployment, but with renewables and nuclear with integrated energy storage. And they found that 83% less transmission capacity would be needed. And so that reduces the overall system cost. So when we've talked to nuclear utilities that see the future of deploying a lot of additional renewable energy, and they're looking at what type of nuclear asset they want to include in that portfolio, this provides them a way to use that energy storage and leverage it with the renewables to reduce the overall system cost. So I thought that would really pertain to this audience because it, you know, reduces the amount of transmission capacity that you need. So that would improve resilience for sure. So that's just another example to think about. So hopefully that gives you a little bit of additional information on kind of what's happening in the nuclear industry. There's lots of different small modular reactor designs out there that do lots of different things. And I'm the type of person that thinks that we need a lot of them to succeed, not just our design. So I hope that that does happen. So thank you.